Okay, this video is on symmetry, and so when we look at symmetry of equations, and we're looking at equations, not functions, because you can tell that this first one here is not a function, okay? But that is what gives it its x-axis symmetry, because the graphical test for symmetry is if the point xy and x negative y are both on the graph, then it is symmetric to the x-axis, okay? Because, for instance, here, if I have the point 1, 1, come on, and I have the point 1, negative 1, both of those are on the graph. And so that's how we can tell for x-axis symmetry. For y-axis symmetry, looking at this one, not sure what I did there. Sorry. Hold on. We have the points x, y, and negative x, y are both on the graph. Okay? So, for instance, in y equals x squared, like this one, we have negative 1, 1, and so we have negative 1, 1, and we have positive 1, 1 are both there. And so we have the x is negative 1 and the opposite of that, so that the opposite of x would be positive 1, are both on the graph. And so that's how we test it for y-axis symmetry. For symmetry to the origin, we are looking at, for graphically, what we test is if the point x, y and the point negative x, negative y are both on the graph. Then we say it is symmetric to the origin. Okay? So for instance, the graph above here is y equals x cubed. And I have the point negative 1, negative 1. And the opposite of both of those, positive 1, are both of those are on my graph. And so we know that is symmetric to the origin. So it's just kind of reflected through the origin. So that is for graphical tests. Now we also are going to have algebraic tests to be able to see. And they're going to follow this same idea, but we'll look at how we do that algebraically. Alright, so here we're going to look at algebraically. And so what I'm going to do is I'm going to take those three equations from above that we looked at, because the first one, and we're going to use that same idea. So we know here for the x-axis, if it's with the x-axis, that xy and x negative y are both on the same graph. If it's the y-axis, it's xy and negative x, y. And if it's to the origin, it's xy and negative x, negative y. And so what we do is if we start with our equation, and so for the equation for the x-axis, that equation was actually x equals y squared. And so if I were to take and replace the y with negative y, I should get the same equation, because my x's don't change. And so if I change this and make it x equals negative y squared, will I get the same thing? Will it come back to x equals y squared? Well, anytime I multiply a negative times a negative, I get a positive, right? So I'm right back to y squared. So this one does work for the x-axis. Let's use that same equation and check it. You're going to test it for y-axis symmetry. So for y-axis symmetry, so we have the equation x equals y squared, and we're going to check it for y-axis symmetry. So here, the things that were different were the x's. It's x and negative x. And so if I replace x with negative x, do I get the same thing? Is x equals y squared the same as negative x equals y squared? And in this case, no, it's not. That doesn't work. Okay. what if I do with respect to the origin? So my original equation is x equals y squared, and if I replace x with negative x and y with negative y, then I still have negative x here, and this will go back to y squared, but that does not give me the same equation I started with. These two are not the same. So it is not symmetric to the origin. So it only worked for the x-axis. Okay? Let's look at another example. Okay, so for the second one, we had y. I didn't want to do that. Sorry. Okay, we had y equals x squared. And so if we make that replacement with x and negative x, then y is equal to negative x squared. And I get kind of the same thing I did over here whenever I was doing x equals y squared, because a negative times a negative is a positive. So I'm going to be right back to y equals x squared. And so these two are the same. So yes, it is symmetric to the y-axis. If I test it for x-axis symmetry, if I have y equals x squared, and I replace y with negative y, I have negative y is equal to x squared, and I can't really simplify it or anything, and so those two do not match. So no, it's not symmetric to the y-axis. If I check it for the origin, y equals x squared, that means I have to replace y with negative y and x with negative x. And so negative y stays negative y. Negative x squared would just be x squared. And so these two equations here are not the same. So this one is not symmetric to the origin either. So it's only symmetric to the y-axis. Then the last one that we looked at was x cubed. Y equals x cubed. And so let's look at it. If I have y equals x cubed, sorry, that is a 3. Doesn't really look like it. And so if I want to check it with respect to the x-axis, remember I'm going to replace y with a negative y. So it's the opposite of what you think it's going to be. So it's going to be negative y equals x cubed. Are those going to give me the same thing? Hopefully you said no. They are not the same. So it's not symmetric to the x-axis. If I check it for the y-axis, y equals x cubed is my original. And so here I would have to replace x with negative x. So y is equal to negative x cubed. Well, that means a negative cubed will be a negative times a negative times a negative, and that would still be a negative, so it would become negative x cubed. Those two are not the same equation, so it's not symmetric to the y-axis. And then finally, we check it with the origin, y equals x cubed. And so here I have to replace both x with negative x and y with negative y. So if I replace negative y with negative y and x with negative x, then I have negative y is equal to, and negative cubed is negative, so I get negative x cubed. Well, that I could simplify because I could divide through by a negative 1. And when I do that, when I divide by a negative 1, I go back to y equals x cubed, and I get the same equation I started with. So it is symmetric to the origin. And so you have these 3 different tests. And so notice on these, for each equation, only one way actually worked. So for x equals y squared, it was only symmetric to the x-axis. For y equals x squared, it was symmetric only to the y-axis. And y equals x cubed was only symmetric to the origin. And so that is the way symmetry typically works. Is it's really going to only fit one of those, but you're going to have to test it for all three, because occasionally you might have one that might somehow work. Okay? It's kind of tricky the way it works, but it could work. Okay? So, I'll give you a bonus buck if you can come up with an equation that will be symmetric to more than one axis, okay, or the origin, so that it will be true for more than one of these choices. So, bonus buck for the first person that can come up with that and tell me what it is, what equation it would be. All right, good luck with your foldable, and we will be using these in class tomorrow, and I'm sorry they're so late.